Chapter 12, The Future of Data Systems. So far in the last 11 chapters, we have had this fantastic journey where we learned through how systems are built today. How are they built to be more reliable, or how are they built to be more scalable, and how are they built to be more maintainable? And in simple terms, reliability is, you can depend on it. It's accurate. Robustness is when you can scale it through the future systems, and maintainability is evolvability of systems. We look through many different types of systems: online systems, analytical systems, batch processing systems. And it's quite important for us to step back and think, if this is what the systems are today, what does the future look like? So let's zoom out a little in this chapter and put everything together, right? Let's look at this diagram here. It is a set of users using all of the kinds of systems that we've talked about so far. And this is the write path in black, and then the brown is the read path, right? So a user on your data intensive web application would write, and there would be millions of these users constantly writing every single minute, every single second, right? You have a lot of data coming in. And so you have the stateless application microservice. We looked at the microservice architecture, why it's important, how it enables teams to develop, multiple teams to develop services that do certain things really well in a stateless manner. We looked at persistent layer with OLTP, transaction processing. So data comes in through your web application service, goes through the application microservice to the OLTP, or the online transaction processing database. This is the persistent store. And typically the write path after the service to the database, there's also an update. And we looked at this specific piece, change capture, which is a major system updating the cache, which is optimized for read, updating various search indexes and clusters, going through various linguist analysis to make sure that you can understand the search terms. You can understand if there is synonyms, and you can understand the language much better. You can extract terms and a whole host of other things to build the index, right? Then you have the cache layer. We talked about that. And then there's async systems, right? Like, let's say someone registers for your website. You want to send them an email welcome notification, right? So there are systems that trigger off of changes that the user writes to your system. So it's email notification system. These are asynchronous systems. Then there's stream processing, things that get you data really quickly in a matter of seconds, so that you can act on it. So there's stream processing systems. Then we looked at OLAP systems, online analytical processing systems, which helps the data analysts to run various queries, the program manager to understand business trends, insights. So there's this warehouse. Then we looked at the batch jobs that are like replacing the warehouse in a pretty big way. We looked at the online key value stores, which are just dumps that can be read off again by the read path, right? So the write path, there's so much going on, so much data moving through various systems, and this is what the chapter calls data flows. It's very important to zoom out and map out whether there's a one-way traffic, or are these systems writing to each other and they're circular and there's no clear ways to understand what's going on, right? So to zoom out, to write down what does your write path look like and what does your read path look like. So the read path again has the same stateless application microservice, and then it queries the search cluster, so the search index. It uses some sort of a query extractor, and then has some federation layer that knows, hey, I'm going to talk to this service for the extraction, I'm going to talk to that index to get this data, and then I'm going to match all of this, I'm going to rank them with this machine learning model that I have, and I'm going to return just the 10 results, because it could have thousands of results, right? So then there's federation layer, and to send the notification, there's also like a Google and Apple involved to actually send the notification. There's also a lot of new systems being built around React, which introduces a lot of state on the client. So heavy clients, a single page application is another, it's a reality almost. Many big websites today use it, where a lot more state is pushed to the client. Offline systems like the email, Outlook, and others, they support multiple state management on the client. There's client-side cache and a whole host of other technologies coming in. So the future in blue, there's a lot of new things coming. And it's quite important for us to understand, hey, how is my data actually flowing? Is it flowing in the right way? Is it flowing in the right, is the right source of truth actually set up the correct way? And so it's important to actually draw it out when you design a system, as to what is your write path, what is your read path, and how all of this actually comes together, and what happens when there's a failure. Because this could be just system in one data center. What if there are multiple data centers connected? What does that stream look like? We looked at all of that in previous videos. So it's quite important, to take time to zoom out and then ask the fundamental question, hey, is this the right setup? Is this optimizing for my use case? So far, 12 chapters has taught us to really read between the lines. For certain design decisions that are taken, is the right system actually being used? Is the right open source technology really used for the use case that you're trying to solve for? So hopefully we can ask better questions, we can make better decisions once we understand at least the high level how the logs are structured, what kind of latency to expect, what kind of throughput, and a whole host of other things. And that'll make us more capable when we have to make a decision between cost for performance versus availability. What trade-off am I okay with, right? Are you okay to optimistically write more to your database than what your data can actually handle? For example, let's say you're Amazon and you have 10 orders, each requesting to order, let's say, 1 pen, but you only have 5 pens in your stock. Would you still process 10 orders when you only have 5 pens? Same example. That's optimistically writing, saying, hey, I'm going to actually allow for these 10 transactions to go through. I'll stock up. If I can't stock up, I'll actually send an apology email saying, hey, we couldn't get you by this time, but we'll actually get you by that time. Same. What are your business decisions that you're optimizing for? It's very important. Airline reservation system, right? They have more bookings typically than the number of seats, but they know that people cancel. They know that they have policies in place to refund and give you credits and a whole host of things. So your website also, you need to design for those system and flows as to what happens when something fails. How does the recovery look like? Is it okay for it to be automated, or does it have to be manual? Because there's cost for it to be automated as well. So with all of these 12 chapters, we have actually equipped ourselves to better understand these trade-offs so that the user actually gets the right experience, right? Take one example one more time. We discussed this previously, but let's say you have a user who's registering, and then the registration, there was some problem. But then the user found out that there was a problem, but then there was some partial data written to the database. And then the change capture caught it, and then the email and notification got to the user saying, hey, welcome, right? And the user saw an error, but he or she also gets an email and a notification saying, hey, everything went through, welcome. So there's a disconnect. There is no causal mapping between what the system thinks it is and what these other systems are telling the user, right? The asynchronous system is telling the user that, hey, everything's good. And the online system is telling the user, hey, there was a problem. So it's very important for us to understand these abnormal situations as to how these conflicts happen, and then what are the decisions that we're optimizing for, so that we'll choose the right system for our use case, right? Same thing could be much more worse. Like, let's say I took an example of Fidelity account that I created, and it gave me confirmation that everything went through, but I couldn't see it in my account was not visible, and so I tried to recreate it, and lo and behold, I found out after 10 minutes that there are 2 accounts created. So I had to go through the customer service. I had to actually tell them to cancel. They tell me, hey, the cancel will take so many days, but you can actually hide them, and a whole host of other things that I spent my time as a consumer. Would you want all your consumers to face that customer service route, or would you want your system to be capable and robust so that emails are not sent or notifications are not sent when there's a failure, or you don't keep sending, let's say, thousands of emails because there was some problem and now you send 1,000 emails for one email that should have gone out? That's a big problem. So once we understand these systems as to what are the trade-offs between cost, performance, and we'll make the right decision. That's the key learning for us to know, and we'll be ready for the future, right? So we went through the system, we went through the read flow, write flow, we understood why it's important. Let's go through some of the other important points that are in this chapter, right? So we should be able to read between the lines, especially use our judgment, right? The other main important piece is there's ACM Code of Ethics for software engineers. It's very important to understand that human judgment is very important, right? we should all read ACM Code of Ethics. It's only after this book that I found out about it. I was trained all throughout, but I didn't actually, read this. So now I read it, and it's quite important to understand that human judgment is important, how you should be constantly evolving and learning, how it's important for you to build the right products with the right constraints. It talks about the interests of the public. It's very important for us to know. That'll also get us to do the right thing, right? You will capture the data for the right amount of time. You'll not overstore, not overtrack, and build all kinds of surveillance that the user is not consented for. Remember, when the user has to consent, they don't really go through hundreds and hundreds of pages, but they depend on you as a software developer to build the right system. So it's all of us who are responsible to build the right system to purge data when we don't need it, because that could be used in many different ways that the user did not intend to give us, right? So since they don't understand what the data consent they're giving us, they probably just say, hey, I accept. But that doesn't mean that we don't understand. When we build our system, we need to put ourselves in the shoes of that user who's using this website. Would you want your data to be used like the way you're using for your users? If not, it's very important for us to use the right judgment and actually go deep and read the 8 principles that are in the ACM Code of Ethics. And that'll get us to do the right thing, right? It's quite important to treat privacy and tracking quite seriously. Like the Industrial Revolution got us a lot of goods, technology advancement, but it had an impact on the environment and pollution, right? Similarly, we are currently in this data revolution, the information age, big data systems, right? But then the casualty here for us is a lot of tracking. A lot of users are tracked. Unnecessarily being tracked. And so it's very important for us to build the right system. There's regulations in place, but you and I are all responsible to build the right level of tracking for the right use case and only use that for those use cases, right? And actually enable the systems so that we don't build echo chambers, we don't have biases that are exaggerated. And especially when you're using predictive analysis with all of the systems that you put in place, think about it. It uses past data to codify what was happening and then to use that as future signals. There's a lot of positives to it, but how you use it, there could be a thin line on actually making it worse and worse for the user versus actually helping them out. So very important for us to not build echo chambers that are spiral death traps, right, for users. And to understand that everything that we do, there are unintended consequences. So for each of us to learn systems thinking, understand what we do, how it impacts the user, but also how it impacts second and third order effects of what we do, right? It's quite important for us to make sure that we think from the human lens in mind, that our algorithm, when it says no to the user, is actually depriving that user from that capability. So it's quite important ethically. It's quite important for you and I to build a system that our future generations would be proud of, saying, hey, they took care of the data. Like we would say right now, hey, pollution should have been taken care of. Similarly, it's very much important for us to build the right level of tracking, understand ACM Code of Ethics, and actually implement it. So coming back to some of the other systems, right? There are other topics that were covered. Total ordering is hard and costly. And so why is that, right? I diverged a little bit into the end parts of this video, but like total ordering is important, right? We covered that in the previous videos, is to have a very clear linear segment of how certain things happen in certain period of time, and then there is a clear distinction on which event happened before which event, right? It's hard. Think about it. If you have multiple services and they are taking writes and they are across multiple data centers, you're going to have multiple leaders. And when they both write, then there's bound to be conflict, right? So scaling is a big part. Microservices enable for those stateless communication. So coordination is possible, but it's very costly. So there could be outages because you have a lot of coordination, because the systems can't be upgraded at the same time. But at the same time, you could have customers who have failure situations that are not optimal either. So choosing the right balance is quite important. But there are systems that we can build today that don't heavily rely on distributed transactions, but depend on the asynchronous log-based ordering mechanism to actually support that transaction level guarantees. So let's take an example. Let's say I want to debit $10 from my account and give $10 to my wife's account, right? So it should be -10 for me and 10 for my wife, right? So let's take this example. So, and let's see how we can do this without transaction support, right? So, distributed transaction support. So, there are two things we need. We need a log which has a total ordering, which is a clear order of as to what event happened, when it happened, right? And then we need a consumer that is idempotent, right? So basically, it you run the same function over and over, it produces the same output, doesn't keep incrementing. It has this concept of deduplication when it's idempotent, right? So, and then the concept you use for ordering log events is this unique request identifier. Let's say everything had a unique ID, right? See, the fact that I want to take $10 out of my account and give it to my wife, let's club this into R1. This is request 1, right? It's the unique ID for what I'm trying to do, right? So let's call it R1. R1 is a debit of $10 from A, which let's say me, and credit of $10 to B, right? All good, right? Now, that is one atomic commit. When you have to write this information, it has multiple things that it needs to do within, but you codify that into R1, which is some unique identifier that says, hey, request 1 says they want to do this, right? And then now you derive two transactions out of R1 unique identifier, T1 and T2. So R1 D1 is basically saying, hey, debit $10, and it could be handled by some other partition. And R1 C1 is basically says credit $10 to my wife, and then it has a separate partition which is crediting. So there could be two different partitions, but the fact that they're both joined with this unique identifier R1 makes it easy for the consumer to make sure that they're not doing the same transaction twice. So let's say after the debit has gone through and then the consumer crashes, so it's going to replay. So when it replays, it finds out that, hey, R1 T1 was already done, right? So it doesn't do that. And then it finds out R1 C1 was not done, so it's going to do it first time. And so it'll only happen once because it has this unique identifier. Now it's part of the total log and it's derived out of that. So when you do that, you can enable for distributed transaction, you can have failure support, you can guarantee exactly once when it does deduplication, right? So it's quite important to do this in the right way, because it's okay for eventual consistency, which is basically saying time gap between which the partitions are actually consistent. But it's not okay if there is integrity issues, means there's data loss, or there is failure to actually, if you see a bank account and if you see the credits and debits don't add up, then that's a problem. That's integrity problem. There's a data loss problem or correctness problem. That shouldn't happen, right? So it's quite important for us to do this. But in a sense, this entire book, right, is actually unbundling databases. That's another big section of this chapter, because think about it, right? When you have to, I took an example here. So if you had to create like an index, let's say you wanted to create an index, right? How do you do it, right? You take a database, you take a snapshot, and then you filter out certain things that you need, and then you build, run some NLP-based algorithms on top, extract, and then you clean up the data, right? So what you do, you create that from a snapshot, you patch, and then you have a merging mechanism. There's going to be an index that's actually batched updated, and there's an index that is live update, right? And so then you want to merge them, and you typically use a federation layer on top to actually merge the two, right? On a high level. Same thing the database is doing, right? So the database, when it wants to create a replica, what does it do? It actually takes the snapshot, and then it actually does all kinds of copy, and then it does the merge, and then eventually catches up, right? So the entire book, right, in terms of how it's scaling up, think about it. The database was doing a lot of things. We talked about triggers, right? Change capture, right? UDFs, right? All kinds of custom logic that stream processors are. So database did a lot of that into one system, and we're trying to break it down into multiple systems so that we can actually scale it up. Why are we doing this? We're doing this for one reason, so that the system that's actually broken down can do that one thing really well. Remember the Unix architecture example in the previous videos, right? All of those commands, they do that one thing really well. Similarly, if we build a stream process that is so good, right? And if we can build a cache that is great, and then we have a change capture that is perfect, captures and updates all of those downstream systems, it doesn't have the penalty or doesn't have the bottleneck for what a single source, single database has, and that's where the future lies, right? So the future has a lot in the pipes, right? We are actually going to be seeing unbundling of the database, right, into systems that actually do those things well. We would have causal relationships that are actually mapped so that we don't end up, bombarding our users with error situations and having them to call customer service or have them see hundreds of emails when they should only see one email, right? So that's where the future lies. The future also lies in terms of how we have heavier states that are now maintained on the client. So it's much more responsive. If you look at a React application, you quickly see how responsive it is, right? Offline support is another big one where your data systems need to be able to support for that. WebSockets is another great technology to Google about and find out as to how those streams of data can be actually be pushed instead of being pulled, right? So there's many new things coming into the future. Offline is another big one that I'm really excited about. And then the last piece, which I shared in the earlier section, is do the right thing. Learn about ACM Code of Ethics. Use your right judgment. Store data that you need. Make it very clear. Put yourself into the shoes of the user that's actually going to be impacted by the decision. If you're a credit card company, this becomes even more important. Say you never approve a credit card for someone because something happened in the past and they'll never get that opportunity. So you and I, it's very much important to build right, robust systems that are right for the planet, right for the ecosystem, right for humans. It's in the public interest. So it's very important for us to design the right system, build it right, but also build it in such a way that the future generations are proud of what we built for them. And that's about it. If you like this video, then tell me in comments what other books you would want me to do. I really enjoyed sharing all of this. You can find the slides of all of this content linked in the description section. I'll also going to be writing down all of the notes at some future point. Thank you for joining. Until the next video.